Good morning, everybody. Welcome again for this new colloquium from the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Elisa Delgado Mena from the Instituto de Astrofísica y Ciencias do Espacio, Universidad do Porto in Portugal. And she will talk about the impact of stellar composition from galactic chemical evolution to planet formation. So Dr. Delgado Mena will be properly introduced by Isabel Marquez. Isabel.
Hola, René. Thank you very much. Thank you, all of you. Welcome again to another web document, in this case, an online colloquium. And first of all, thank you very much, Elisa Delgado Mena, for having accepted our invitation to give this colloquium. Elisa Delgado Mena obtained her PhD in 2011 in the Instituto de Astrofísica de Canarias, the IAC in Tenerife in Spain, where she studied the chemical abundances of light elements like lithium, beryllium, carbon, and oxygen in the atmospheres of exoplanet host stars, and also how the formation of planets can influence such elements. After that, she carried out her research with the FCT postdoc fellowship in the Center for Astrophysics in the University of Porto in Portugal, the CIUP, from 2012 to 2016. And then she got an IFCT contract in the same university. And she's author of more than 100 papers in peer-reviewed publications since then. Her main research interests are the derivation of stellar chemical abundances of solar-type stars, planet host stars and M-dwarfs, the search and characterization of exoplanets, especially around evolved stars, stellar variability and atmospheres, and the chemical evolution of the galaxy. And today, as you know, because of the title of the talk, she will be talking about the impact of stellar composition from galactic chemical evolution to planet formation. I say it again, it's a pleasure for us to have you here, Elisa Delgado, with us in virtual format, and thank you very much. The floor is yours.
Okay, so let me also thank you for the invitation. It's very nice. And I'm sorry I'm not in person, but okay. Okay, I will start with seminar. I'm going to touch different themes, different points that I have been following during my career, since I have studied mostly the chemical abundances, but with different aspects, and how they can help us to study different fields within astrophysics. So why these chemical abundances are important? Well, they are needed to understand how the galaxy was formed, the different components of the galaxies, and also to understand the nucleosynthesis processes that gave rise to these elements, which in turn are needed to understand the galactic chemical evolution. Also, we need to know the chemical abundances from stars to do a proper classification of stellar populations, and also, for example, with the techniques of chemical tagging. Chemical abundances can also be complementary to the studies of astroseismology and also to better understand stellar activity in stars. They can also be used to determine distances and ages. And last but not least, they are very important to detect and characterize exoplanets. We need to know the stars that host exoplanets in order to correctly characterize such exoplanets. So in this talk, I'm going to focus in these two aspects of how the chemical abundances can help us to better understand these two things that I'm pinpointing here. Okay, so as you can see, the composition of the Earth compared to the one of the universe is quite different. And we need to know the composition of different things or different sites and to understand all the processes that go from one to the other. So it's obvious from how the percentage of elements in the universe are distributed that a long chain of events need to happen in order to arrive to the composition of the Earth crust. So this is being studied under the galactic chemical evolution. And for this, as I said, we need the chemical abundances of the stars. So how do we know how the elements are formed? So initially, at the beginning of the universe, there was just hydrogen. And then the first elements were formed in the primordial nucleosynthesis. So this happened just very short after the Big Bang. where we have helium, deuterium, and a small quantity of lithium. So the initial universe was mostly formed by hydrogen and helium. So then where do the rest of the elements come from? So the answer is in the stars. This is through stellar nucleosynthesis. So at the beginning, the first elements were formed by very massive stars that died a long time ago. These were very massive stars with very short lifetimes that released the first metals into the universe. Later, the next generations of stars were processing this material and created more and more metals in the universe to reach to the proportions we can observe now. And by decades of studies and having proper chemical abundance studies of stars, then we can reach to this nice periodic table where we can know much better what are the different nucleosynthesis processes contribution to different elements. So from supernovae, merging neutron stars, or just the slow stellar nucleosynthesis happening during the evolution of such stars. But to reach to this, as I say, we need to have precise abundances. And for this, we need high resolution spectra. And with high resolution, I mean usually about 40 or 50,000. Also, you can do things, of course, with lower resolution. There are many elements which have very weak lines or that are only accesses when you really have high resolution. So it was in the early 90s where there started to appear studies with a significant number of stars, like this seminal work by Edwardson et al. In 1993. Where the abundances of alpha elements and other elements were shown versus the metallicity. This is the typical way of representing the abundances. So usually you have the element versus the iron as a function of metallicity. And the metallicity is used as a proxy of evolution because it's a very easy element to determine in stars. And usually we compare the stars with respect to this element. So these earlier studies already show that these alpha elements, which are the elements produced by alpha capture reactions, so oxygen, magnesium, titanium, silicon, they show an increasing trend for smaller metallicities as the metallicity decrease. So why this happens? Okay, so this is due to the stellar nucleosynthesis that happens in massive stars that is burning consecutively more and more elements with these alpha captures. And then we have these reactions that give rise to these elements, magnesium, silicon, sulfur, titanium. And just before the stars explode as supernova type 2, the massive stars, this is more or less the structure they have. So when they explode, apart from the explosive nucleosynthesis that happens during the explosion itself, you also have all these elements that are released to the interstellar medium. On the other hand, the iron and the iron peak elements are mostly produced in binary systems. So these are exploding white dwarfs that have a companion in a binary system. So these are lower mass stars. And because these two processes happen at different scale times, then we have this balance. Because massive stars have shorter lifetimes, so then they release their products in the early universe, so at lower metallicities. So then at lower metallicities, we have this higher contribution from massive stars, so higher alpha abundances over iron. However, as the time passes, and then you give time to the low mass stars to die and release these elements to the universe, then you get this balance of both elements, and then this is what is called the knee, then you have the ratios that are equal. In more recent years, with the access to much higher precision and higher resolution spectra, we have been able not only to see this increase, but also to see the differentiation between the populations in the galaxy. So this study was the first one from Adivekian et al. In 2011, showing a new population of stars that are called high alpha metal rich stars that are clearly separated from the thick disk stars at the same metallicity, and that is not clear whether they are an extension of the thick disk or they are a different population. So if on top of the abundances, we can also have the stellar ages, then this really opens the door to a more insightful view on galactic archaeology. So in the last years, there have been great advances because many large surveys have been producing very nice results. like LAMOS, Apogee, Gala, Kepler, Gaia ISO survey. So then with this, we can study the contribution from different nucleosynthesis sites. We can study them at different places in the galaxy, and then we can see how they vary with the age and the metallicity. And this gives constraints to the models of galactic chemical evolution. So as I said, with this work that was presented in 2011, this was the first work on a series that we have done together with colleagues. Here, these are the alpha abundances that are the average of magnesium, silicon, and titanium. And here we can see the separation that I was telling you before. So these are the thick disk stars that are older. And these are these high alpha metal rich stars that are like a new population, and the thin disk stars. And these purple ones are halo stars. So although we have had a lot of results from these surveys that are very important, because these previous surveys are mentioned, because they are tracking stars that are far away also. So we can also have a much broader picture of the full galaxy. However, we also still need smaller samples, so this one that has around 1,000 stars with very high precision abundances, because the spectra has very high signal to noise. And here I'm talking about resolution. The HARPS spectra has a resolution of 100,000. So we can get much better precision. And the disadvantage of this is that these are based on the solar neighborhood only. So then we don't have information from stars that are farther away. But still, these kind of studies are still very important to do a better calibration of these galactic chemical evolution models. We have also studied heavy elements, so those that are created with neutron captures, for example, copper, zinc, but then also these S-process elements, and you can see that they have a different behavior. Here I'm using similar, so you can see the similar separation for some of the elements, right? So for example, for zinc, that behave similar to alpha elements, you have this thick disk and the high alpha metal rich stars that are quite well separated. Also in the copper, we can see this. Then for these other elements, the S process, you can see that the production of these elements it increases with metallicity, with a maximum around solar metallicity. And on top of that, you can see galactic chemical evolution models from different authors. So for some of the elements, the models work quite well compared to the observations, but for others, this is not the case. So then having this kind of studies is really useful to improve such models. And I will mention especially that more work is needed at higher metallicities. So for example, this sample that we have using is very good in that sense, because it has quite metal-rich stars. So it will be nice to see what's going on here. So these heavier elements are formed in younger stars, so in stars that release their products later in the galaxy evolution. So they are the products of the low mass stars that produce these elements during the AGV phase, during the thermal pulses. And these are the elements that are called the slow process neutron capture. Then, on the other hand, there are other elements that are produced during the explosion of the core collapse supernovae, like europium, by the rapid neutron capture process. And then also recently, thanks to different works like the ones from LIGO, for example, it has been seen that also the neutron star collisions have a strong contribution to the R process. And they can create some more exotic elements like golden, silver, platinum, but also radioactive elements like thorium, uranium, and so on. So not only we study the elements with respect to iron, but also the elements between them, so different abundance ratios, because when some of these elements, for example, europium and oxygen that I'm showing here, although both of them have a major contribution, especially oxygen that is mainly formed in massive stars. So both of them have a strong contribution from massive stars. By studying the trends with metallicity, we can maybe infer more information about the progenitors. So for example, here at lower metallicities, we see that europium is lower than oxygen because it's negative. So then it means that the progenitors of producing oxygen are probably more massive and then die earlier and release this oxygen into the interstellar medium than the progenitors producing europium that probably are of lower masses. And then with other elements, we can do similar analysis, especially with those ones that are produced in a single site, as happened with oxygen. That is mostly 100% is formed in massive stars. We have also added the ages because, as I told you, this is a very important piece of information to really better understand the galactic archaeology. So for this sample, we have also derived ages just using parallaxes from Gaia and magnitudes and the parsec isochrones using the param interface. And then we were able to have a nice sample, reduced sample with errors in ages smaller than 1.5 gigayears. Of course, this is not fantastic. This is not like having ages from astrophysicology, but I think it's the best we can do at this moment with this kind of stars. And although iron has been used typically as an age proxy, you can see here that in reality is not. So there is a decreasing trend of metallicity with age. So older stars are less metallic, but you can have for the same age very broad ranges of metallicities. And later it has been shown, not only by these works made by us, but also, of course, many other works, that however, the alpha over iron ratios are much better age indicators than metallicity. You see the dispersion here is smaller. And for example, you can observe here that this abundance is increased faster, let's say, with age. So this is showing that in the thick disk, that are these blue stars, there was a more intense star formation rate. Also, we can add the age in color scale to see how the populations in this abundance versus iron plane, how the age can give us more information. So, for example, here the thick disk stars have all a similar age, so they are very old. These are the limitations of this method to get with the isochrones, that we just go to the very high ages. There is not many difference between them. But then for the thin disk, we can see really a very nice stratification. So the youngest stars are the ones that have the lowest alpha over iron. And then as you, for the same metallicity, as you go to older age, to higher alpha ratios, you are also seeing older stars. And we can also see that these high alpha metal-rich stars have similar ages as the metal poor thin disk stars and similar alpha content. So the age is important to also have extra information. And this age is very important also to try to use the chemical abundances by themselves as age indicators. So there's certain chemical abundance ratios that I will mention now. So for example, here with other elements, not only alpha, you can also observe very nice trends that thanks to this high precision of the data we have in the solar neighborhood, because we have very good spectra, the stars are bright, then we can really see this stratification in ages as the abundances vary. For example, if we compare aluminum and zinc, we see that they have a very similar behavior. So the abundances increase as metallicity decreases, because these elements are forming massive stars. And then we can also see that the age has an effect here. So older stars also have higher abundances for a same metallicity. We can also observe, for example, that for the S-process elements like strontium, yttrium, and barium, the maximum production is obtained at solar metallicity. This is something that the models more or less represent quite well. And this production is made by the youngest stars that are in the solar neighborhood. And these trends of the abundance ratios with age can help us to have an alternative way of determining ages, which is using this so-called chemical clocks. So these are ratios of elements that have a strong dependence with age. So the idea is to mix elements that have a decreasing trend with age, like strontium or yttrium, with elements that have an increasing trend with age, like magnesium or other alpha elements. Because this, for example, strontium or yttrium are S-process elements that are formed by lower massive stars, then they increase with age. So younger stars have higher values. However, for the elements produced by massive stars, then the abundances increase as the age increases, so for older stars. However, the first studies that were using these chemical clocks as a proxy to get an age were being used with calibration formulas that are the same for all the stars in a given sample, but without taking care of the metallicity. And the metallicity is very important, as you can see here, because the slopes are not the same depending on the metallicity of the star, so the behaviors are different. So we have to take into account this. Okay, so with this, I'm finishing the part on galactic chemical evolution. And now I will talk more about how the chemical abundances can help us understand the planet formation processes and can help us also to characterize the planets. So because planets are formed in protoplanetary disks around their stars, they are made of the same material as the star was formed. So initially, you can logically, one could think that the composition of the planets is linked to that of their stars. So to date, more than 5,000 exoplanets have been discovered. Here you can see a plot for exoplanets archive. The increase of planets has been exponential with years, especially after the Kepler launch. And in this other plot, you can see how different detection methods can prove different regions in the mass period diagram. So some techniques are more sensitive to planets that are farther away, others are more sensitive to more massive planets. So it's needed to have different kind of methods to try to populate this diagram. In order to get the abundances of the stars, we need a spectra. So most of the studies are based on these radial velocity planets, but also for the transiting planets, we also have a lot of good spectra, and we can use this information to better characterize these planets. So when the first surveys of systematic search for planets were started in the late 90s and the beginning of the 2000s, one correlation started to show up that now is very well established, which is the giant metallicity correlation. So here what it's seen is that the stars that have planets, giant planets, have a distribution in metallicity at larger metallicities than those that don't have. This has been observed by different studies, and now it's accepted that this is this has like a primordial origin. So in the sense that you need to have a high metal rich content in order to form giant planets. Later studies were focusing more in less massive planets, because as the techniques improved, then we were able to discover less massive planets like Neptunes or super Earths. And here the correlations are not so clear. So different works by different authors found, for example, this one with Kepler. This is based on radii, but not instead of masses, showing that the metallicity distribution of these small planets is similar to the field stars. Then this is with the HARPS and Coralie radial velocity surveys. These are the distributions of these smaller planets. And also the metallicity is not as clear as for the planets that have higher masses, so giant planets. So then maybe for these stars, for these planets, is not so critical the metallicity. Then later, the next step was to not only check the metallicity, but to check individual elements. So can we know more about these formation pathways by studying the different abundances? So the first studies doing this didn't find very clear correlations, because they were based on small samples. And many times the comparison samples, so samples that don't have planets detected, were not properly characterized, or they were not good to do this kind of studies. But this thing changed with this HARP CTO sample that we have also used for the galactic chemical evolution studies, because we have a very statistically significant sample in terms of numbers. So with a lot of stars where we have searched for planets and giant planets have not been found. So we know that these stars don't have planets, giant planets at least. And one very clear thing that was found in 2012 was that the stars that have planets, that are the red and the blue ones, have an increase in the alpha over iron abundances as the metallicity decreases. So it seems that, so the red points are the Jupiter hosts and the blue points are the Neptunians. So this points to the fact that maybe when the quantity of iron is not very high, then you need to compensate it with alpha elements. and alpha elements in this case are in this plot are titanium, magnesium, and silicon. So, and this is something we know, right? The most important elements for planet formation, as we see in the Earth and in other rocky planets, are the iron, oxygen, silicon, and magnesium. So this might be a way to overcome this lack of metallicity, lack of iron. Then you can compensate it with these other elements. We have also tried to do this for other elements that a priori are not maybe so important for planet formation, like these heavier elements. In some cases, what we are seeing is just that, for example, we found that planet hosts have a higher abundances of zinc, but this is not because zinc is an important element for planet formation, just because it has a similar galactic chemical evolution as alpha elements. So you need to consider the galactic context for comparison purposes. It's not only just comparing the abundances per se. And it's important to compare the abundances at the same metallicity, because like that you are a bit diminishing the effects of galactic chemical evolution. We have tried to do the same with carbon in a more recent paper, but this element is harder to determine and the errors are larger. So we don't have so many stars. So we've also found hints that carbon can be important at lower metallicities, but this is at the borderline of being statistically significant because of the low numbers I told you. And also with oxygen, we find a tentative indication that these abundances also increase. But of course, with oxygen it's even much worse because this is a very difficult element with very weak lines and the abundances have very large errors. So this is something that was also discussed in the paper by Haywood 2009, how the increase of abundances at lower metallicity points that these planets, these lower mass planets, are easier to form in the thick disk than in the thin disk, because in the thick disk you have larger amounts of these alpha elements. But okay, so with these abundances, we can also try, so not just to do population studies in terms of general samples of planet hosts, but also try to understand better the planets from an individual point of view. This is the typical radius mass diagram for exoplanets, where these lines show different internal compositions. So there is a degeneracy. Planets with similar density can have different compositions. So by using the stellar abundances, using them as a proxy for the bulk composition of planets, we can try to better constrain this composition and try to understand better what is the internal structure of these planets. One of the pioneering works in this topic was made by Bond et al. In 2010, who was using stellar abundances to create protoplanetary embryos. And then with dynamical and chemical embodied simulations, he was creating the possible planets that could be formed around such stars at different distances to the star. And then with this, you can determine the bulk composition of these planets. And then what they observe is that with the range of stellar abundances that we have in the samples with planets, you can have a wide range also in bulk composition for the internal a bulk internal composition for these planets. And especially there are two elemental ratios that are very important to determine how it's going to be the internal composition of such planets, which are the carbon oxygen and the magnesium silicon. So the carbon oxygen controls how the oxygen can be distributed in silicates. So because if you have a very high CO ratios, you almost don't have oxygen to form silicates, but then you will have carbon-rich phases such as graphite and some carbides like silicon carbide or titanium carbide. However, for most of the planet hosts, and so for the stars, we find CO ratios below 0.8. And this means that then the mineralogy will be controlled by this magnesium silicon. It will control how the distribution of the elements are made by different silicates. So for example, when you have a magnesium silicon ratio lower than 1, then you have mostly pyroxene, and then the excess silicon is going to form feldspars. Then when you have close ratios above 1, then you have magnesium that is mainly distributed between olivine and pyroxene. And then when you have very high ratios of magnesium silicon that are not observed, then you have all the silicon as olivine. And these silicates so they will shape how the crust and the mantle composition and the different layers are formed. However, at this point, I want to warn about, so we have to be careful with these stellar abundances, especially with the carbon-oxygen ratios, when you want to use them to understand the planetary composition, because especially with oxygen, it's a very tricky element, and then we have a lot of errors, and then there are systematic. So here we saw how the CO ratios, as a function metallicity, depend a lot whether you are using one oxygen line or another oxygen line in the stellar spectra. So for when you are using this line that is known as the forbidden line, you can have very high CO ratios that probably are not real, right? You see the errors are very large. However, when you see this other oxygen indicator, then you have a lower dispersion. And most importantly, you don't find very clear systematics between stars of different temperature. Here we see that cooler stars, that are the green points, have much larger CO ratios. And this is caused by the abundances themselves because they have a strong dependence on age. So it's important to try to use the best oxygen, the best abundances you can have access to, but also to minimize the systematics. It's good also to measure the solar abundances in the same way as you measure the carbon and the oxygen, and then you cancel out the systematics due to the methods and the model atmospheres. So with these elemental ratios, the carbon, oxygen, and the magnesium silicon, we can obtain more insights about internal composition. So the carbon and oxygen are a bit tricky because since they have low condensation temperatures, then this CO ratio in the planets, it's more dependent on the distance to the star where the planet was formed. However, in the case of the iron, magnesium, and iron silicon ratios, there are more constants because these elements condense, let's say, fast in the planet formation phases. So they are more similar to the stellar values, and this has been observed in the solar system, where these ratios are quite similar between the Sun, Mars, Venus, and Earth. However, for carbon and oxygen, it's not the same, whether your planet was formed farther away than after the snow line, or it was formed closer to the star. And the use of these bulk iron and silicon ratios, it's very useful to reduce the 16th degeneracy in the internal structure of planets and to constrain much better the planet composition. So these are the typical models that are used, are kind of, let's say, simple models. So they are considering a core formed by iron and an iron alloy, so either nickel or sulfur. Then you have the lower mantle, the upper mantle with different kind of silicates, as I explained before, and then you can add to your model a layer of liquid water or even an atmosphere. So can we use the stellar abundances as a direct proxy of the bulk composition of planets? Well, this can be done initially with the rocky planets, because then, first of all, you remove the outer layer, so you don't have to worry about the atmosphere. So, for example, this nice work by Schulze et al. In 2021, they calculate the core mass fraction from the stellar abundances of the stars with the core mass fraction of the planets obtained just from the mass and the radius of the planets, assuming a simple model in which you have a planet with a solid iron core and a mantle with oxidized silicate, so no iron in the mantle. And then they found that distributions of these core mass fractions in general are indistinguishable between the star and the planet, except in very few cases, in only 2 of 11 planet cores that they studied. In one of them, for example, they found that the core mass fraction of the planet was much higher than that of the star. So this was hinting that probably this is a super Mercury planet, so planets that have a very high density. And on the other hand, they found another case in which the planet has a much smaller core mass fraction of the star. So this is a low density small planet that are still not clear how they can be formed. Also, in this work by Divekian et al. In 2021, there was made an homogeneous study with stellar abundances of planets and their stars. and using only planets that have very low errors in mass and radius, so below 30%. So what they did was to compare the iron to silicate mass fraction of the stars with that of their planet. You can see it here. So this is the iron mass fraction of the planet, and this is the one of the star. And they found that there is a clear correlation between the both of them, although the values are not exactly the same. So the correlation is not 1-to-1. And there is this group of planets that are that have a very large core mass fraction or iron mass fraction. So they are very dense for a given iron mass fraction in the star. It's true that they are mostly formed around stars with a higher metallicity, but they are clearly separated. So for these ones, we have to be more careful when trying to extrapolate the stellar radius to the ones of the planets. Also, we can study the planetary bulk composition of the protoplanetary embryos or the seeds that are going to give rise to planets, but in the galactic context. So this was the work done by Santos et al. In 2017, where they compare, just by using the abundances of iron, magnesium, silicon, carbon, and oxygen, they derived the core mass fractions and the water mass fractions of these stars, and see what will be the hypothetical planets that you can form there. So the seeds of possible planets change it depending on the population where the star belongs from. So they found that, for example, in the stars that are in the thick disk, that are these light blue ones, have a larger content of water. And this is mostly due because these stars in the thick disk have larger amounts of oxygen. So you can have protoplanetary material with a larger amount of water, and in principle, you can form planets with a higher water fraction. On the other hand, you can see that the stars that are in the thin disk have larger iron mass fractions because the quantity of iron is larger. So it's important also to study the different populations of planets we can have depending on the galaxy position of the stars. This has also been done by Beach and Battistini, and in this case they were seeing this composition of the protoplanetary embryos, but outer and inner to the CO line, and they saw, for example, that the planets that are formed farther away in the disk have a strong dependence with metallicity in terms of the water mass fraction that are these points. So as you go to lower metallicities, then these planetary building blocks have higher amounts of water. It's also important in terms of stellar abundances to study the radioactive nucleides. In this sense, there are very few studies because these elements are difficult to determine. But they are very interesting because they have an important impact on the plate tectonics and the volcanisms, and this in turn can impact the planet habitability. And also other works have, like this one by one, have explored the use of europium abundances as a proxy for radiogenic heat, because since europium has a similar chemical evolution as thorium. But since thorium is much more difficult to determine, then you can use these europium abundances to better understand also this other factor in the planetary formation and evolution. So not only the abundances can have an effect of the planet formation, but also the planets can affect the stellar abundances themselves, because there can be accretion processes. I'm not mentioning here, but there are many studies on the TC trends, so how the condensation temperature of the elements can affect the abundances that you observe in stars that have accreted or not material. And then you can also study the effects on light elements, like lithium and beryllium, because these elements are very easily destroyed in stellar interiors, and they are more prone to mixing processes that can happen inside of the star. And these mixing processes have a strong connection to the angular momentum history of the stars. So we found, for example, regarding lithium, we found that the stars that have planets are depleted in lithium, but only around solar temperature stars. So in a very narrow range where the convective envelope has this size that can be sensible to this planetary formation processes affected the angular momentum evolution. And also other studies have found that the most lithium-depleted stars also have fewer refractory elements. Also, you have a broad range of lithium abundances for a given age. That is also another factor that can affect these lithium abundances. So it's quite hard to disentangle these effects, and it would be ideal to have to study these abundances in very young planet hosts when these interactions between the disk and the star are still taking place. So what we observe is that the stars that have larger amounts, so that have a bigger mass, so giant planets, have show this stronger effect with lithium. They have more depleted abundances. There can also be an effect at later phases of evolution. So the lithium-rich giants that are stars that are not supposed to have high values of lithium because it should have been destroyed after the RGB phase. But then some of them show high lithium abundances, and some of the theories that have been put on the table is that the accretion of planet engulfment of planets when the stars expand in this RGB phase can cause this increase in lithium abundances. And okay, now I'm going to briefly mention the M dwarfs because, as you have seen, I have been talking only about FGK stars, that are the stars that we can better characterize. We know them quite well, and the spectra, it's clean and it's nice, I would say. But then we have the M dwarfs that are a mess, and they are much more problematic. So in the optical, there are a lot of molecular absorption that depress the continuum. There are these molecules, so all the lines are blended. It's very hard to determine not only parameters, not only abundances, but also the parameters. And you can see this nice study by Vera Passayer in 2022 that did a comparison of different methods from different groups for a sample of stars observed with Cármenes. And they found that, okay, for the temperature, there are more or less agreements, and the techniques can get more or less good values. However, for the metallicity, there is a big mess. And I'm not talking here about gravity because it's even more complicated. But there is a degeneracy in the models, in the spectra, in the synthesis spectra, or in different methods, that you can have this degeneracy in temperature and metallicity, and also with log-G providing similar spectra. So then it's very hard to disentangle these parameters. And we will need to improve these methods because many of the current planetary search surveys are being done around M dwarfs, because since they are lower mass stars, it's easier to find lower mass planets. So the possible Earth 2.0 should be around an M dwarf. There have been very nice advances in the last couple of years. Here I just mentioned a pair of papers used with the spectra from Cármenes and from Apogee, where they were already able to determine individual abundances. But as you can see, this is the same plot I was showing you before. So in the background, you can see the FGK stars, and this is for the Ms. The errors are huge. So of course, it's very difficult to say here to which populations these stars belong from. And then, of course, using these abundances to constrain the planetary interiors, it will be much more difficult because the errors are very large. But very nice works are being done, and others that are in process. So I think this will really improve in the next year, especially with the use of near-infrared spectra, because in the near-infrared, you don't have so many molecules, and you start to see isolated atomic lines. So that gives access to the derivation of individual abundances. And just, I will make a bit of publicity of a catalog that we have in our institute that has been an effort of many years. So all these trends that I have shown you in this plot that we have done, it's we were able to do them because we are analyzing big samples of stars, and all of them analyzed in the same way, in an homogeneous way, trying to use a spectra of similar quality, and of course using the same tools. So this is very important to really try to find these correlations between abundances and parameters like the planet metallicity correlation. So when you mix determinations from different teams, then it's difficult to see these effects. So we have this catalog that it's publicly available with stellar parameters for a large sample of planet hosts, mostly FGK. And we are planning in the future to complement them also with stellar abundances. So this can be useful also for the community to study also the internal composition of exoplanets, of rocky exoplanets, as I showed before. Okay, and just the conclusions. So just to finish, so as I have shown, the determination of chemical abundances is critical for many fields in astrophysics. We need very high resolution and high signal to noise to resolve some of the atomic lines for specific species like oxygen. It's very tricky, or some of these exotic elements, heavy elements. We also need to study the stars at different metallicities to understand which different processes take place in different parts of the galaxies and at different timescales. And in what regards the planets themselves, it's clear that we need very precise stellar characterization, not only to just determine the mass and the radius of the planets, which are dependent on the mass and the radius of the star, but also to understand the composition, the formation processes, and even the evolution of such planets. The studies have shown that you need a minimum quantity of metals in order to form planets. I think the lowest metallicity planets, the lowest metallicity of the star hosting a planet is around -0.7. So it seems that it's hard to form these planets below this limit. But this lower quantity of iron can be compensated by other elements important for internal composition, like the alpha elements, magnesium, silicon, oxygen. And these elements are important not only to unveil the bulk internal composition and the structure of exoplanets, but also to understand other processes like volcanism, the plate tectonics, the radiogenic heat, and so on. Okay, and this is everything I have to tell you. Thank you.
Thank you very much, Elisa, for this wonderful talk. So now I will pass the word to Pedro Amado. He will manage the question and answer sessions. So Pedro, go on, please.
Yeah, hello. Thanks, Rene. Thanks, Elisa, for this very nice talk. We open this round of questions for people attending the seminar. I myself have a few, mainly from the last part of your talk. So maybe to open fire here, I will start with my own questions. You show here in these conclusions that stars need to have a minimum quantity of metals, to form the planets. We need some amount of dense material to form a core of at least 10 Earth masses to then start accreting gas to form the giants and so on. But we also know that there are planets that have been found around stars that have very low metallicity. When I did this in the 2018 workshop, so it's been now some time, and this field advanced very quickly, I found that there were around 15 systems with metallicities less than 0.7. One of them was, I think, if I remember properly, Captain Star. So, so do you think that in these cases, of course, if everything is correct, if the metallicity has been measured correctly, if the planet has been detected correctly, if it is not something else like a magnetic activity or whatever. So do you think these other elements could be playing a major role in the formation of these systems?
Yes, well, okay. What I have said is based, of course, in the core accretion theory to planet formation, because there is also the gravitational instabilities that, as far as I remember, doesn't have so much strong dependence on metallicity. So, okay, I said -0.7, but I didn't remember exactly about these values. I don't know if these 15 stars that you say are all M dwarfs, or are also FGK stars. I remember that some years ago also there even was a claim about a planet form in a halo star or very far away star, but then later it was refuted. If this
is Captain Star, I think it is the one you're mentioning here.
This is an M dwarf, right?
Yes, exactly.
Yes. Okay. So the problem of the M dwarfs is that right now we cannot compare the metallicity scales. They are different, or at least we are not sure they are the same. That's why it's so important to improve these methods, and it's needed also to. So I think the infrared is going to give us a nice opportunity to test. So to try to compare if the metallicity scales for FGK stars are the same in the optical and in the near infrared, and then try to expand this to the M dwarfs. But since the way these metallicities are measured are much more degenerate, I don't think, I mean, the errors are still quite large. So I don't think you can say, okay, because the metallicity of this M dwarf is minus 0.8, then this means that the planet is not real. No, maybe it can be. And then probably this planet belongs to the thick disk, because we have seen that, at least in the HARP CTO, that as long as you go to lower metallicities, all the planets are in the thick disk, especially those with the lower masses. So maybe, yes, you can have a smaller metallicity, but then you need to compensate it with other material to form the planets.
Yeah, and just now you have been mentioning this possibility of using near-infrared spectrographs to determine the metallicities or some of the abundances for these stars, for M dwarfs. I haven't seen many, or I haven't seen works doing this. Of course, I haven't followed much the results on this line. You will know much better than I do. Is it so? There haven't been many works on using near-infrared high-resolution spectrographs to determine metallicities, or?
So, for example, you have Cármenes that I guess people in the Granada know very well, and there are many studies with Cármenes, but they have been mostly using not so much the far near infrared, but closer to the red part, so the redder part of the optical. But there are also works by Vera Passeyer using the near infrared. And now there are later works by people in the Complutense, for example, also using the near infrared part. There are the works from Apogee, but the problem of Apogee is that lower resolution is only 22,000, so maybe the methods are not comparable. Then there is this very interesting paper of the Japanese using Cármenes spectra that show that, I think it's this one, that is very tricky because the atomic lines are sensitive to changes in abundances not only of these elements, but also of other elements. And this is something that in the FGK stars we don't see, so it's much, this this is much more difficult to determine individual abundances. And then we have always talked about the planet metallicity correlation in terms of what we know for FGK stars. But then we really need to set a correct scale. So you can find studies in the literature that have systematically M dwarfs with very low metallicities. In others, they tend to find higher metallicities for all the stars. So there is a very big dispersion in the results. And maybe one way to overcome this is to try to study with the same techniques, although it's not really exactly possible to do it, but to use both FGK and EMS in the near infrared to study both of them. This is something we want to do, and I think some people also from Spiru has been doing that, the Spiru spectrograph in Hawaii, to try to compare these abundances and try to get better parameters. So then we need to use the binaries, the FGK plus M binaries to do this, yes.
Yeah. Well, yeah, when I was saying that there were not many works, of course, I'm completely biased, and I was meaning outside.
Okay. No, yes, there are. You have these people from Apogee and Spiru,
okay.
and also with Characterise, there were studies in the past. And now NIRPS has started working. So we will also use NIRPS data to analyze this, and it will be very nice to compare the results to what has been obtained with Cármenes.
And Characterise is back to the telescope. Ask Characterise Plus. Or,
yes, Characterise Plus. We also
offer of near-infrared spectrograph there to do this kind of works.
Yeah, sure.
Okay, I'm gonna give the audience another opportunity to ask a question. I have
I
a
had
third
a
one.
question, another question. Can I?
Go ahead, Mayra.
Yes, I understood that all these studies has been done for the cases N, K star, low mass star, and mean. Which are the prospect for the cases B or O star in terms of the abundance, in terms of the planet formation, perhaps? Could you comment a few words about this? Stars, massive stars?
Okay, so for massive stars, I never studied them, but I know they hardly have atomic lines, right? So except for the OV stars, I don't know. I don't know lines more than hydrogen, helium, and maybe some metals. Then you can get abundances for the AM stars. So these are the A stars that are usually magnetically active. And they are peculiar because they have strong lines, and then you can check the abundances of these stars. But these are special stars, so I don't think they are being done studies of abundances for planet purposes around these stars. And then on the other hand, the planet formation around massive stars is still not fully understood because there are not many planets discovered for stellar masses above 3 solar masses. So these are BS types, let's say. Then to discover these planets, we have to go to the Wolf counterparts, so to the K giants, where we can apply the radial velocity and the transit method. And some planets have been discovered, but the planetary frequency really drops down after 2-3 solar masses. So then you can, in these stars, you can study the abundances in the giant stars, not the light elements, because they are processed inside of the star, and then you cannot get the abundances that were supposed to be in the protoplanetary disk, so carbon, oxygen, nitrogen. These abundances change. However, the alpha elements are not so affected. And then, yes, you can also compare you could compare also the abundances of these elements to try to correlate to the formation of this star. But this is more for A stars and the revolve counterparts. For O and B, I don't think there are many studies. There is now a survey that is called BEAST that is starting to find planetary bodies, or probably brown dwarfs, with direct imaging around. There was a discovery around a 9 solar mass star, but of course this should be or try to be confirmed by other methods, not only by the direct imaging, and to see if this is really a brown dwarf, or is even a low mass star, or yeah. So it's really hard to find these planets.
It's very challenging, no?
It's very challenging. Yes.
Study these kinds of stars. Thank you.
Thanks, Mayra. Any other questions? If there aren't any, I have one that maybe we can extend it offline. So briefly, Elisa, well, we are trying now to constrain planetary interiors of terrestrial planets, especially in M dwarfs, particularly here. We are trying to do that, but of course, the only way we have now is trying to get ratios of metals, no? Like you have mentioned, silicon and magnesium with respect to iron from the star, and then assuming that these are the same for the planet, and this will help us constrain these planetary interiors. What are the steps, if any, that are still missing, or that is preventing us from doing this more precisely or better than we are currently doing?
So if I remember well, so to constrain the internal composition of planets, I think the most relevant parameter is the radius of the planet itself. This is the one that is going to mostly affect the density, and then in turn the composition. So if you have a large error in the radius, I think it doesn't matter so much the abundances. However, when you have a good precision in radius, and this is something that is being achieved now with TESS and with Cheops, and in the future with Plato, then the abundances will play an important role. But still, an error in the abundance, I don't remember the numbers exactly, but the typical errors we have can suppose an error in the let me show, for example, this one. Okay, so these are planet hosts, which very good spectra and high resolution, and with a very careful analysis. And this is the errors in the iron mass fraction of the star. So still, you see, you have an error. It's smaller than the one in of the planets, because it's very dependent on the radius. But still, you have this error. And this is for FGK stars. Then for the Ms, here the errors in abundances are really very small, maybe 0.05 dex. Then if you go to the Ms, as I show here, the errors are 0.2, 0.3 dex. So I don't know now the right number, how it translates into the core mass fraction, but maybe the core mass fraction can change, I don't know, from 30% to 30 to 40% or 50, and it changed a lot. So I think it's still hard to use these ratios for M dwarfs, and I think it's easier to get a more precise mass and radius than the information from the stellar abundance side. But in the future, of course, I think this will improve. Hopefully, it will improve.
Yeah, we hope so. Thanks, Elisa. I don't have any other questions, and I don't see any hands raised from the audience. So we thank you once again for your nice talk. So I give you applause.
Thanks a lot. And sorry if this was very dense. Maybe I touched very different things, and I didn't have time to explain all the things in detail. But I think it's nice to have a broad view of what we can do with chemical abundances and how important they are for many different fields in astrophysics.
Sure, I think it was probably enough to interest many people other than us working in M dwarfs or planetary studies. Thank you again, and
Okay.
I pass the floor to Isabel.
I'd like to thank you again, Elisa. It's been a pleasure. Your talk, I mean, very dense. You can understand it. For me, it has been even more difficult because it's a completely different field. But I found it very interesting. So thank you very much.
Okay, thank you also. Okay, so we will meet next time.